This is the ALU of my homebrew 8-bit CPU. We've been busy building up this ALU and making it more powerful. And in the last episode, we've added a whole bunch of flags to the ALU. So the ALU now tracks if there was a carry output in the previous operation, if the result was 0, if it was negative with the sign flag, or if an overflow happened. Today, I would like to expand on this and look at what kind of conditions we can detect just by looking at the flags. In the previous episode, we've used this table of x86 jump instructions as a kind of inspiration for what kind of flags would be useful to have in the CPU. So let's revisit this table, and this time let's take a closer look at the actual jump instructions and what kind of condition or comparison result that they represent. The first few jumps look pretty straightforward. Basically, you can look at one individual flag, and then depending on whether the flag is 1 or 0, you can perform the jump. So it would make sense for the CPU to be able to do the same thing. We want the option to look at each of the individual flags and then do something if that flag is 0 or do something if that flag is 1. Let me create a new text file and let's start making a list of all these condition codes that we would like to support. The first 8 condition codes will basically check each of the 4 CPU flags to be either 0 or 1. Looking back at the table of x86 jump instructions, we can see that the 0 flag is actually the first case of a flag that indicates an interesting condition in the CPU. Specifically, if we execute a compare instruction, which is just a subtraction in the ALU, if that subtraction is 0, the left and right hand side operands were actually identical. They subtracted to 0. So if we run a compare and the 0 flag is set, that is an indication that the two sides of the comparison were actually identical. And so in this table, when the 0 flag is 1, this is not only a jump if 0 instruction, but this is also a jump if equal instruction. So let's add an equal and not equal condition code, which looks at the 0 flag. Now this is pretty straightforward for equality and inequality because we can just check the 0 flag, but there are a whole bunch of other comparisons we would like to do. And if I scroll down in this table a bit, you can actually see that there's a whole bunch of jump instructions, and there seems to be 2 flavors, one for unsigned numbers and one for signed numbers. And so instead of trying to make sense of every single jump instruction in this table, let's actually write up a few example comparisons that we might run on the CPU, and let's think about what kind of flags come out of that operation, and then determine what kind of conditions we can detect based on those flags. So in my CPU, when we're running a comparison between A and B, we're actually doing a subtraction between A and B. We're subtracting B from A. And so as a first example, let's think about what happens if we compare the value 2 to the value 2. Let me write down the left-hand side A input in binary. It's just the number 2 in binary. And the right-hand side B input is negated, so that's the value -2 in binary. And this gives us an all 0 result with the carry flag set. And this is what you would expect if you compute 2 minus 2. You want to see 0 as a result. And in this case, the carry flag is set because we're doing a subtraction and the right-hand side is in its 2's complement form. As a kind of interesting aside, when we do subtraction, the carry flag is actually more like an inverted borrow flag. So we're going to expect the carry flag to be set and the 0 flag to be set because the result is 0. And the sign flag to be 0 because the sign is 0, and the overflow flag to be 0. Now let's try the case where the left-hand side is greater than the right-hand side. Let's compare 2 and 1. So in this case, because we're computing 2 minus 1, the result is actually 1, and the carry flag is set. And in this case, we expect the 0 flag not to be set. Let's try the opposite. Let's try a case where the right-hand side is greater than the left-hand side. Let's compare 2 and 3. And in this case, the result looks quite a bit different. We're getting the result -1, which is what you would expect. It's 2 minus 3 that we're computing. And -1 in 2's complement is all bits set in the result. And this time the carry flag is not set because of how 2's complement arithmetic works. And again, the 0 flag is also not set because the result is non-zero. But now the sign flag is set, and the overflow flag stays at 0. For comparisons between unsigned numbers, these are actually the 3 interesting cases. We have both sides being equal, the left-hand side being greater, or the right-hand side being greater. A first interesting observation to make here is that the carry flag is 1 in the case where both sides are equal, or the left-hand side is greater than the right-hand side. So the carry flag being 1 here seems to indicate that the left-hand side is greater or equal to the right-hand side. And the complementary is also true. The carry flag being 0 seems to indicate that the left-hand side is less than the right-hand side. But what if we want to check that the left-hand side is strictly greater than the right-hand side? For this, we can just check the carry flag being 1, because that would include the case where both sides are equal, but we instead have to check that the carry flag is set and the 0 flag is not set, so we have to explicitly exclude the case where both sides were equal. But this then allows us to do an unsigned greater than comparison. And similarly, if we want to check whether the left-hand side is less than or equal to the right-hand side, we check that either the carry flag is not set, which is the less than relationship, or the 0 flag is set, which is the equals relationship. Let's compare this with the x86 table. In our case, greater equal means the carry is set, and less than means the carry is not set. And interestingly, in x86, it's actually the exact opposite. Jump if above or equal or greater or equal is actually checking for the carry flag being 0. This is actually due to a quirk in x86. x86, when it does a subtraction, inverts the carry going into the adder and inverts the carry coming out of the adder, such that you can interpret the carry flag as a borrow flag. Big shout out to Artentus, who has pointed out that quirk in x86 in the comment section of the previous episode. Thanks a lot. So apparently for subtractions and comparisons by extension, x86 has an inverted carry flag compared to my CPU. If we account for that inversion of the carry flag, these 4 lines here actually match the condition codes that we've just added to the text file. Further down, there are 4 more comparison instructions, which are explicitly listed as signed comparisons compared to the unsigned comparisons we had above. In this case, we're not looking at the carry flag because that has a more murky meaning in signed arithmetic, but it looks like we can compare the sign flag and the overflow flag to determine various kinds of relationships between left and right-hand side. Let's go back to a bunch of examples and let's try to figure out how the flags can actually indicate certain relationships among the numbers. To get started, let's do the same comparisons with negative numbers. And again, the result is 0 because we're subtracting -2, -2, and the carry flag is set. Then let's try a case of negative numbers where the left-hand side is less than the right-hand side. And in this case, the carry flag is not set, the 0 flag is not set, the sign flag is set again because the topmost bit of the result is set, and the overflow flag is 0. Then let's try the opposite. Let's try a case where the left-hand side is greater than the right-hand side. In this case, the result is positive, it's the number 1, and the carry flag is set. 0 flag is not set because the result's non-zero, there's no sign, and no overflow that happened. So these are the cases when both sides of the comparison are negative. Let's also try the cases where the left and right-hand side have a different sign. For example, let's compare 4 against -4. And in this case, the result is 8 because we're adding 4 and 4. The carry flag is 0. The 0 flag is not set because the result is non-zero. There's no sign flag and also no overflow occurred. And let's try the opposite. Let's compare -4 and 4. This time we get a negative result, -8. So the carry flag is set because of how the subtraction works. The 0 flag is not set because the result is non-zero. The sign flag is set because it's a negative result. And no overflow occurred. We haven't seen any overflow flags being set yet, so I think it would be good to have a few examples that trigger that. The way to cause the overflow flag to be set is to choose sufficiently positive or sufficiently negative left and right hand sides in a comparison. So let's use the largest positive number, for example. Let's compare 127 to -127. In this case, the carry flag is 0, and the result is non-zero, it's the number 254. However, the sign flag is set. This sign bit being set actually points at a problem. We're interpreting the inputs and outputs as signed numbers, and the left and right hand side inputs were both positive numbers, the sign bits were 0, but now the result has the sign bit set. It actually reads as the number -2. And so our overflow detection hardware will actually detect this and set the overflow flag in this case. Let's try the other way around. Let's compare -127 with 127. And after the computation, the carry flag is going to be set, and the 0 flag is not going to be set because the result is non-zero. It's actually the number 2. And since 2 is positive, the sign flag of the result is not going to be set. And again, this indicates a problem. We added two negative numbers, the sign bits of the inputs were set, but the result has the sign bit cleared because of an overflow. And so the overflow flag will be set in this case. And intuitively this makes sense, we're adding two negative numbers and you expect the result to be even more negative, but in this case it suddenly became positive. So an overflow happened here. So we now have quite a few examples of comparisons between signed numbers where one or both of the operands are negative. And from the table of x86 jump instructions, we know that we probably want to look at the sign and overflow flags to determine which side of the comparison was greater than the other. Let me collect all examples where the sign flag and the overflow flag are both 0 or both 1, so they're equal to each other. Let's go through this and determine how the left-hand side compares to the right-hand side. 2 equals 2, 2 is greater than 1, minus 2 equals minus 2, minus 2 is greater than minus 3, 4 is greater than minus 4, and 127 is greater than minus 127. So apparently the sign flag being the same as the overflow flag indicates a signed greater or equal relationship between the compared numbers. Let's see if the complementary is also true. Let's find all the cases where the sign flag and the overflow flag disagree. And again, let's see how the left-hand side compares to the right-hand side in these cases. 2 is less than 3, minus 2 is less than minus 1, minus 4 is less than 4, and minus 127 is less than 127. So apparently the sign flag and the overflow flag being different indicates a signed less than relationship between the compared numbers. And this makes intuitive sense. If the sign and overflow flag being equal indicates greater or equal, then them being not equal indicates the opposite, and the opposite of greater or equal is strictly less than. And similarly to the unsigned comparisons, we can additionally look at the 0 flag to determine the other two cases. For example, to check whether the left-hand side is strictly greater than the right-hand side, we can copy the condition for greater or equal, but then exclude the equal case by additionally checking that the 0 flag is not set. And then finally, let me copy the strict less than condition, and let me additionally allow the case where both sides are equal by checking whether alternatively the 0 flag is set. And with that, we also get the 4 signed comparisons that were mentioned in this table of x86 jump instructions. And I think that makes us more or less on par with the capabilities that the x86 CPU has that are listed here. Let me do some cleanup and refactoring of the Boolean expressions. And so now with a little bit of Boolean refactoring, these terms actually look kind of similar. Unsigned greater than and unsigned less equal use the same condition, but inverted in one of the cases. Signed greater equal and signed less than also check the same condition, but inverted in one case. And signed greater than and signed less equal also check the same condition, but inverted in one case. So we only really have to compute these 3 Boolean expressions from the flags, and then we can use their results and their inverted results to check certain conditions. And so I think the way I'm going to do this in hardware is I'm going to use a multiplexer to pick between these different conditions and between these Boolean expressions, and then use an XOR gate to conditionally invert them to get all the opposite inverted checks as well. I'm going to make a list of multiplexer terms, and I'm just going to go from top to bottom and fill this in. Before we go through this list, I think it would be good to also reserve a condition code that is always true or always false when we check the inverted version. Let me add a column for which multiplexer input that we're using, and a column which indicates whether we use the inverted version of that multiplexer input. And so first up is this always true expression, which we're going to hook up to multiplexer input 0. And actually, by inverting this multiplexer 0 input, we can get an always false condition. Next up, we want to be able to check just the carry flag. So let me wire the carry flag up to multiplexer input 1, and we'll use it in an uninverted and inverted fashion. Then let's hook up the 0 flag to multiplexer input 2. The sign flag goes to input 3. The overflow flag goes to input 4. Then for equal and non-equal, we're checking the 0 flag, but we already have that. That is mux input 2, so we'll just reuse that. And so equal and non-equal are basically just aliases for checking for 0 or non-0. Same for greater, equal, or less than. These are just checks for the carry flag, which we already have. We'll just reuse input number 1 for this. And now to the first actual expression that we need to evaluate. We have this not carry flag or 0 flag expression. And let's hook that up to input number 5 of the multiplexer. Let me flip those around to follow the pattern. Same with the other ones down here. Next up, we need sign flag XOR overflow flag. So this is going to be multiplexer input 6. And then last but not least, we have this 0 flag or sign flag XOR overflow flag that we need to check. And let's hook that up to multiplexer input number 7. And so any actual hardware on the breadboard and later the PCB, all we need is a multiplexer with 8 inputs, and we're going to wire those 8 inputs up according to this list of multiplexer terms. And looking at the result either in its uninverted or inverted fashion, so by using an XOR gate and an inversion bit, we can check for all these conditions listed up here in the table. So we have a multiplexer select signal. This is a 3-bit signal to pick among the 8 choices. And we have an additional inversion bit here. So we need a total of 4 bits to represent these condition codes here, and we'll use 3 of those bits to pick the right input in the multiplexer, and then another bit to conditionally invert that multiplexer. And then this gives us a signal which tells us whether the conditions that we're checking hold. To make life easier later, let me combine the mux and inversion column here into a 4-bit code that is going to be the condition code that checks for this specific condition. All right, and in practice, we're going to hook the multiplexer select lines up to bits 3, 2, and 1 of the code, and the inversion signal up to bit number 0 of the code. And so with this code, we have a 4-bit number that lets us express any of these conditions that we would like to have checked. And it being 4 bits is quite convenient. It fits into the place in an instruction where the register operands are. And it also fits up into the upper 4 bits of the instruction where the ALU opcode currently is. So after going through this entire exercise of figuring out these condition codes, let's now actually go and build this up in hardware. And let's add these 3 chips to the ALU. Alright, I've already zoomed into the upper part of the ALU, and I think up here in the top right there's quite a bit of room that we can use to build up this condition detection circuitry. Let's start with the multiplexer that lets us pick between the conditions. I'm going to use the 74HC151 chip, which is a single 8-input multiplexer. Right about there looks okay. First up, let me connect power and ground of the multiplexer. And then let's go hook up the different flags and conditions that we might want to check to the inputs of the multiplexer. Condition 0 is going to be the always enabled condition, so we'll hook input 0 of the multiplexer up to just VDD, a constant one. Then input 1 is going to be the carry flag. Input 2 is going to be the 0 flag. Input 3 is going to be the sign flag. Input 4 is going to be the overflow flag. And now we're getting to the interesting part. We have 3 more inputs left, and those are all combinations of the flags that we hooked up. Input 5 will want to be the Boolean expression not carry or the 0 flag. So we'll need an OR gate for that. This is a 74HC32 chip, which has 4 2-input NOR gates. Let me connect power and ground of that. And so let me connect the 0 flag to one of the OR gate inputs. And then the other input of the OR gate we want to connect to not carry. But we don't have not carry, we only have the carry flag itself here. However, we are going to use a bunch of XOR gates to compute conditions, and we can just use another one of those XOR gates, because the chips come in packages of 4, to do the inversion. This is a 74HC86 chip, which has 4 2-input XOR gates. We've already used quite a few of those across the build. And to invert the carry flag, we're going to connect that to one input of the XOR gate. And then the other side of the XOR gate, we're going to connect to VDD, a constant one, such that the XOR gate acts like an inverter. And now let me bring the output of that XOR gate, the inverted carry flag, over to the OR gate, where we already have connected the 0 flag. And so at this OR gate here, we have the 0 flag connected and the inverted carry flag. So the output of the OR gate computes not carry flag or 0 flag. And so let me take that output and bring it over to input number 5 of the multiplexer. Then for input 6 of the multiplexer, we want to compute the sign flag XOR the overflow flag. So let me bring the sign flag and the overflow flag over to the XOR gate here. And now this output of the XOR gate, which holds the sign flag XOR overflow flag, we need to connect to input number 6 of the multiplexer. But we also need it in another term that we compute in the OR gate. We also want to compute 0 flag or sign flag XOR overflow. So let me bring that output over to the OR gate and also to the multiplexer. All right, that's input number 6 of the multiplexer connected to sign flag XOR overflow. And then last but not least, input number 7 of the multiplexer, we want to connect to 0 flag or sign flag XOR overflow. We already have the sign flag XOR overflow on one of the OR inputs, so let me connect the other OR gate input to the 0 flag, which we conveniently already have available on another pin of the OR gate. And the output of this OR gate will connect to input number 7 of the multiplexer. Alright, pretty cool. So that's all 8 inputs of the multiplexer connected. And by picking one of the inputs, we can pick a condition to check. Now, once we have picked one of the inputs and the multiplexer produces that at the output, we also want to have the option to invert that output such that we can check the conditions or the inverted version of the conditions. And to do that, we'll use one of the XOR gates. So let me bring the output of the multiplexer over to one of the XOR gates. The output of that XOR gate is going to be basically our condition, the condition match signal that tells us whether the condition we're checking is actually true and we have a match. Let me add a green LED to that output such that we can observe it easily. And that is basically all we need to compute the various different conditions we might want to check. The only thing left to do is to decide how we're going to drive the 3 select inputs to the multiplexer and this inversion signal to the XOR gate. And then what we're going to do with the condition match signal that comes out of the XOR gate, which tells us if the condition we've selected is actually true or not. And I think the easiest thing to do for us is to just wire that 4-bit condition code, which consists of the 3 select bits of the multiplexer and the inversion signal, to connect that to the ALU opcode. And then we're going to add a 5th ALU opcode bit here at the decoder, and that 5th bit is going to let us decide whether we want to do a conditional move, and the other 4 bits are the condition we want to check, or whether it's just a regular ALU operation and we're not interested in the condition. And so first up, let me add a 5th LED here to the decoder and prepare the 5th input to be connected. And now before we bring the ALU opcode bits up to the selection signals here, we want to take the condition match signal from the circuitry up here and feed it into another input of the decoder, such that the decoder, when it sees a conditional move operation, can actually react to whatever the status of the condition match signal is. And then the decoder can decide whether it wants to perform a move or not. Okay, so this gives the decoder access to the condition match, and it can basically read the status of the LED up here. And now let's take the lower 4 bits of the ALU opcode, treat it like the condition code, and hook it up to the multiplexer and inverter. First up, we've used the least significant bit, bit number 0 of the ALU opcode, as the condition invert signal. So let me bring opcode bit 0 up to the XOR gate that inverts the condition that we've selected with the multiplexer. And then opcode bits 1, 2, and 3, we're going to connect to the multiplexer select lines. Okay, that's everything hooked up to the decoder as well. And now the only thing left to do is to go update the ALU operation decoder. Let me first open up that decoder.txt file, which we've used to define all the ALU operations. The ALU opcode, or the ALU function, used to be a 4-bit field, but we've just added a 5th bit here. So let me add a column in the front. And for all the existing operations, we'll just set this topmost bit to 0. So if we set that topmost ALU operation bit to 0, we'll just get the plain old ALU operations that we had before. And when we set this to 1, we want to do a conditional move, and we'll interpret the lower 4-bit as the condition code that we want to check for. I'm not going to specify the lower 4 bits because this will be the condition code. We basically want to interpret any ALU op that has the topmost bit set as a conditional move. And now the question is, what are we going to fill in the back here for the logic operation? Because the logic operation is the thing that allows us to choose between the RD operand or the RS operand, or perform any other kind of logic operation. And I think what we want to do is, if the condition does not match, we want to forward the RD operand. And if the condition matches, we want to forward the RS operand, the right-hand side operand. And this will have the effect of a conditional move. We're reading both the RD and the RS register. The RD comes in on the left-hand side input, the RS on the right-hand side input. And then if the condition doesn't match, we'll just produce the RD operand and write that back to the RD register, which is basically just writing back the value it already has. So it doesn't do anything in practice. It's as if the move didn't happen. And if the condition matches, we'll forward the RS operand, which comes in on the right-hand side, to the result, which will then look like we moved the value from RS into RD. Let's go change the equations for the logic operation. Since we've added another bit to the ALU opcode, we have to extend all these terms here and additionally check that this topmost bit is 0, because all the logic operations that we have here, they were for the case when the topmost bit is 0 when we're doing a plain old ALU operation. And then let's add the additional terms that are introduced by this new conditional move operation. Logic operation bit 0 remains at 0, so that doesn't introduce any new terms. And then logic operation bit 3 is also trivial. In case the topmost ALU opcode bit is set, bit F4, we just want to set this output. And now to the interesting bits, logic operation 1 and logic operation 2. Logic operation 1 should be a 1 if both F4 is a 1 and the condition match input is a 1. And logic operation 2 needs to be a 1 if F4 is a 1 and the condition match input is a 0. We haven't really introduced any new 1s into the shift operation output, so all we have to do for the existing terms is also consider ALU opcode bit 4. And the same thing for the carry operation. We didn't introduce any new 1s that should be produced at the output, so all we have to do is constrain the existing terms and only make them apply when the topmost ALU opcode bit, input F4, is a 0. That looks good. Let me copy these expressions and then let's open the decoder.pld file, which is the thing that we're actually using to program the decoder chip. And we're going to replace the existing equations here. And this F4 and cont match input that we've wired up to the chip on the breadboard, we'll also have to add to the pin declaration up here. F4 was right next to F3. And we've hooked the condition match signal up all the way at the bottom of the input side of the decoder. Alright, let's run this through the Galette compiler, and then let's check if the pinout is updated properly. And that looks pretty good. We have input F4 wired up to pin 6, and we have the condition match signal wired up to input 9, which matches what we have done on the breadboards. So let me get the decoder chip off of the breadboard, and then let's write this new configuration to it. Let's give this a try. First up, let's check the easy condition codes, the ones that check the individual flags. Let me wire up a flag swap operation here at the decoder such that we can store a value into the flags, and then we're going to see whether we can make sense of that value through the condition codes here. This is the flag swapping operation. As you can see, flag swapping is enabled. And so let me set the lowest bit in the left-hand side input such that we can store that into the registers, which is going to set the carry flag. We have to enable the clock and then actually toggle the clock. And that sets the carry flag in the flags register, and all the other flags are 0. Now let me switch the opcode to the very first conditional move operation we have. And I just realized that the multiplexer has an enable input that we need to tie to ground. And this looks pretty promising. This is condition code 0, which is the always condition, the one that is always true. And so correspondingly, the condition match turns on. And based on this condition match, which feeds into the decoder, we should be able to observe different result patterns of the ALU. The pattern you can see right here is the one I've hooked up to the right-hand side input of the ALU, the RS input. Let's try the opposite. Let's try condition code 1. This is the never condition, which is always false, because we're still selecting input 0 of the multiplexer, which is always a 1, but then we're inverting it through this least significant bit here, and so the condition never matches. And as you can see, the pattern showing up here at the ALU result is no longer the right-hand side input, but actually what's connected on the left-hand side. This is the pattern that we used to store in the flags register through the flag swap before. Pretty sweet. Let's try condition code 2, which is the carry condition. This selects multiplexer input 1, which is the carry flag, and produces that as a result. And since the carry flag is set, the carry condition is true, and we actually perform a move. And then condition code 3 is the not carry condition. We're still picking input number 1 of the multiplexer, which is the carry flag, but then we invert it through the XOR gate and the least significant bit, and this produces a 0 at the output. So because of the carry flag being set, the not carry condition does not hold, and we don't do a move. We just forward whatever's in the RD operand as the ALU result. Let me set the 0 flag through a flag swap. And if I pick the carry condition code, the condition is false because the carry flag is false. And when I pick the not carry condition code, the condition is true because the carry flag is indeed not set. Let me pick the 0 condition code, and this condition is true because the 0 flag is set. And the not 0 condition code is false because the 0 flag is set. Let me set the signed flag. And if I check the 0 condition, the condition is false because the 0 flag is not set. However, the not 0 condition is true because the 0 flag is indeed not set. Let me pick the signed condition. That condition is true because the signed flag is set. And the not signed condition is false because the signed flag is set. Last but not least, let me set the overflow flag. Again, if I check the signed condition, the condition is false because the sign bit is now cleared. And if I check the not signed condition, the condition is true because the sign bit is indeed not set. Let me pick the overflow condition, which is indeed true because the overflow bit is set. And the not overflow condition is false because the overflow bit is set. Let's quickly check if a few of the more complicated condition codes work. For example, let me try the unsigned less equal condition code, which checks for not carry or the 0 flag. And this condition is indeed true because the carry flag is not set. And conversely, the unsigned greater than condition code is false because that's the opposite. Let's try the signed less than or equal condition. This condition checks whether either the 0 flag is set, which is not true, or whether the sign and overflow flags differ, which is true in this case. So the condition holds. And the signed greater than condition, which is just the exact opposite, does not hold. And we can also check the signed less than condition, which just checks in isolation whether the sign flag and the overflow flag disagree. And since that is the case, the condition is true. And the signed greater or equal condition is false, conversely, because that's just the opposite. And just as a quick demonstration of what the ALU decoder picks for the logic operation down here, currently the condition is false, so the decoder picks the RD logic operation down here, which just forwards the left-hand side to the result. If I pick a condition that is true, however, you can see that the ALU decoder now picks the RS operation down here at the logic block, which just forwards the right-hand side input, the RS input of the ALU, to the result. Alright, I think that's all the ALU changes that are needed. In the next episode, we're going to integrate the ALU back into the CPU and figure out how we'll drive this 5th ALU opcode bit from the instruction bits. Once everything is put together, I want to sit down and write some fancier tests for these conditional move ops that we've just added. I'm pretty sure we can cook up something nice there. I can't wait to finally push this over the finish line. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you again next time.